All right, good afternoon, guys. Today I'm going to be continuing our discussion on confidence intervals. Today we're going to be looking at um, confidence intervals for two populations. And I'm going to do two examples with you. Um, the first one's going to be about two samples that have means. And the second example we're going to do is number 3 on the assignment, which is a two proportion example. But both examples use the panic model. Okay, so and as we're going through the problem, I'll just be breaking down what changes are going to happen because there's definitely going to be some changes when we have two samples to work with instead of just one. And I'm also going to be showing you a couple of methods just basically for this lesson, because for this lesson with two samples the calculations get a little bit more complex in a way, but I'm going to show you guys a website that can kind of do the work for you. And so let's go ahead and look at the first example in our assignment, or the first problem in the assignment. So it says, a dietitian has developed a diet that is low in fats, carbohydrates, and cholesterol. Although the diet was initially intended to be used by people with heart disease, the dietitian wishes to examine the effect this diet has on the weights of obese people. Two random samples of 100 obese people each are selected, and one group of 100 is placed on the low-fat diet. The other 100 are placed on a diet that contains approximately the same quantity of food, but is not as low in fats, carbohydrates, and cholesterol. And what they did with each of the 100 people, they measured the amount of weight loss or gained in a three-week period, and they got the following results. Okay, so the 100 obese people that were on the low-fat diet had a mean weight loss, an average weight loss of 9.3, with a standard deviation of 4.733, and those other 100 people that were on the other diet, so there's two diets here, lost an average of 7.4 pounds, and with a standard deviation of 4.037. So they did the data for us, right? They took all the data and they did the calculations for us. And so what they're giving us here, let me point this out here, the 9.3, for example, is our x bar, but I'm going to call it x1 bar. And the other mean over here for the other diet is called x2 bar. Okay, and so instead of just having one x bar, one sample mean, we have two. Okay, and this makes sense more in a clinical setting or scientific setting. Two sample confidence intervals make more sense because when you're trying to compare, two types of drugs, two types of diets in this case. So this makes sense more in the clinical setting. Okay. The next thing is that they gave us the standard deviation. So I'm going to call this S1 and S2. Standard deviation 1, standard deviation 2. And it's up to you, how you want to choose to number them. You can say the low-fat diet is my group 1 and the other diet is group 2, or vice versa, right? You can say the other diet is 1 and the low-fat diet is 2. It's up to you. Here, the only difference is how we're going to use these numbers, right? We're actually going to find a difference between, right? Because when you're experimenting, you want to know, in this case, you want to know which diet is better. Which diet causes the most weight loss, right? So we're going to calculate a sort of a difference here, a subtraction. And if you subtract a bigger number minus a smaller one, we get a positive value, right? if I subtract a small number minus a big number, I get a negative value. So my concern here is, what's the difference going to be? Okay. So let's go ahead and start the acronym, right? So first, the acronym is P. And the question, sorry, I forgot to mention, the question is, or the instructions are to form and interpret a 95% confidence interval for the difference between the population mean weight loss for the two diets. Okay? So how many parameters am I interested in? In 2. So in this case, we're working with 2 means. We want to know what's the true mean weight loss for the low-fat diet, and what's the true mean weight loss for the other diet. So we have 2 variables here. We took 2 samples, 2 parameters. All right. The next thing I want to talk about is the assumptions. Okay, that's letter A. And so I want to break down, what are we going to write, or what are we going to talk about in the A of the acronym, in the assumptions. So first of all, we want to check, was the data that was collected, was it collected from 2 random samples? So same idea when we took 1 sample, right? We checked to see, was it a random collection? Okay. Number 2, what are we checking for? Normality. Okay. So you can either, apply the central limit theorem, but this time we're going to apply the central limit theorem to the sum of the sample. Okay. So if we took 2 samples, we took sample 1 and sample 2, and remember, for the diets we sampled 100 people for each diet. So here we're looking for normality based on, is N1 plus N2 greater than or equal to 30? Is N1 plus N2 greater than or equal to 30? That's the central limit theorem applied to 2 samples. Okay. The other way we can check for normality is if they gave us the data. And so if we look at the problems in the assignment, like problem number 2, problem number 4, I think it's just 2 and 4. So number 2 and number 4, where they give you the data, we can probably graph that data and check to see if that data forms a normal shape, right? Okay. And then the third thing that we check for in the assumption step is to check to see if each population needs to be at least 10 times the sample size. This is the step where we would write, it's safe to infer that there are at least 10 times n people in the sample, or 10 times n people in the population to ensure independence, right? So this, let me just state it here. This is the 10 times n situation. Okay, but you might ask, well, don't we have 2 n's? We have 2 groups, 2 samples? Yeah, in this case, what you want to do for this step is figure out which of the 2 samples was larger and multiply that times 10. But for the diets, we selected 100 people for the low-fat diet, and we selected 100 people for the others. So both n's are the same, so it's going to be 10 times 100, right? Okay. So this is breaking down step A. So let's go ahead and work out step A, see what it's going to look like. Okay. So step A, number 1. And let me go ahead and write it out here. So I'm going to put number 1. It was given in the text that both samples that were collected were random. if you go back and you read through the text, it'll say that the 100 people were selected randomly. Number 2, both samples are very large, so the central limit theorem guarantees approximately normal distribution. So here, I would check what's n1 plus n2, which is 100 plus 100, which is 200, which is definitely greater than or equal to 30. Okay, so that's step 2. Step 3 of the assumptions is to check, is it safe to infer, is it safe to assume that both populations are at least 1,000 people, right? How did we get 1,000? We did 10 times n, which gives us 1,000, right? The next acronym in PANIC is the letter N, and that stands for the name of the interval. What are we going to call this interval? Well, the name that we're going to use is the two-sample T interval. Two-sample T interval. Two-sample because we're collecting two samples. T, why do we use T? Anybody remember? Why do we use T? Let me get a different color here. So we're using T because we were given S, well, S1 and S2, the standard deviation from the sample. That's mainly the reason, is because they're giving us S1 and S2. As a side note, when would I use Z interval? When would I use Z interval? Well, if I'm given sigma 1 and sigma 2. So what's the difference between S and sigma? S is the standard deviation that you calculate from the data. The standard deviation, sigma 1 and sigma 2, is given from the population. Okay, so we just mentioned that again. S1 and S2 come from the sample data. Sigma 1 and sigma 2 come from the population data. So what's the main conclusion here, right? We use the T interval if we're using sample data. We use the Z interval if we're using population data. Okay. Let's look at the next step. Next letter is I. And so we're going to do a calculation in this step. I like to call this the calculation step. So another thing that's going to change is the formula. It's going to change the following way. Okay. So we're drawing two samples here, one of size n and one of size n1 and one of size n2, right? From populations that are normal. So how does that change from a 1 sample to a 2 sample? Okay. So one thing we can see is that instead of having one mean, we have two sample means. And what are we doing to the two samples? x1 and x2. The averages of the two samples, x1 bar and x2 bar. What are we doing to them in this formula, right? We are subtracting them because we want to know the difference, right? Which one has a greater weight loss? Okay, let's see. T stays the same, but there's going to be one minor change here because when we would find T before, we would need to find the degrees of freedom. And remember, the degrees of freedom was n minus 1, but what do we do if we have two n's? And the other thing that changes is the standard deviation becomes the following. Okay. So this is also in your formula chart. If you want to look in your formula chart and see how the standard deviation changes for two sample proportions. But let's go ahead and see what happens in our calculations, okay? So, let me go ahead and circle, it for you. Okay, so this standard deviation here will change to this. So this is the standard deviation, or I think they call it standard error for one sample. And this is the standard error for two samples. All right, so let's see. So in step I, I'm going to write the formula. I'm going to substitute my x1 bar minus my x2 bar, plus or minus, and the degrees of freedom is 193. And this is where you might wonder, well, wasn't degrees of freedom, let's talk about that a little bit. Wasn't degrees of freedom, wasn't it equal to n minus 1? But what was the sample size? It was 100, right? So what's 100 minus 1? 99. Okay, so then I had some students say, well, so maybe it's the degrees of freedom is n1 plus n2 minus 1. Okay, that's a good hypothesis. So let's try it out. 100 plus 100 minus 1, that's 200 minus 1, which is 199. Okay, that's close, but the true degrees of freedom is 193. And you might ask, where did you get that number from? And I'll show you, and you can see in your PowerPoint that in the PowerPoint, you see degrees of freedom is the following formula, this big calculation here. So it says we never want to overestimate the accuracy of a t procedure, so we choose n minus 1 of the smaller sample size. Or if a calculator is available, we use this. Now, this is going to lead me to the next topic. Is I'm going to share with you guys a link to a website that kind of does the calculation for you. And that way, because I'm more concerned with the conclusion than the calculation in this case for this topic for two samples, because like I mentioned, the calculations here get more complex, and I don't want you to have to worry about the calculation part, in this case, more the interpretation. Okay, so let me just finish talking about the calculation and the conclusion, and then I'll show you guys a little bit of how the website works that I'm going to share with you guys. Okay, so it's plus and minus t. We get this t value because we get the following, degrees of freedom. Remember, it said we can use the 100 minus 1, which is 99. So if you go to your chart, let me actually pull it up. If you go to your chart, remember we're doing a 95% confidence interval, and 100 minus 1 is 99, so I'm going to choose 100 from the table, and that leads me to 1.984. Okay, 1.984. So that's where I got this 1.984 here. Okay, go ahead and delete this. Okay, so the rest is just plugging in. S1 was 4.733 squared, then divided by 100, plus 4.037 squared divided by 100 gives us a lower and an upper bound of the following. And so our conclusion is we are 95% confident that the true mean difference, notice that it didn't just say true mean, the true mean difference, because we're subtracting, right, lies between 0.673 and 3.127 pounds more for the low-fat diet than the other diet. How do I know which one it's referring to, right? Well, what was the average weight loss for the low-fat diet? It was 9.3, right? What was the average weight loss for the other diet? 7.4. So who had a higher weight loss, right? The low-fat diet. So we're going to say that the difference created a positive difference because we subtracted the low-fat diet minus the other diet. So there was more weight loss for the low-fat diet than the other diet. Okay? All right, the next thing I want to talk about is the website that I'm going to share with you guys. So let me pull up a browser here. Let me go to that website. All right, so this is a website that I found that calculates the confidence interval for 1 or 2 samples. Okay? 1 or 2 samples. So for this case, we're not working with a single group, we're working with 2. So I'm going to click that box, that bubble there that says for difference between 2 groups, right? And it opens this. And so are we looking for the difference between proportions or means? I'm going to say for means. Okay. And we're going to go ahead and leave it as absolute difference. Relative means percentage difference. We're not interested in the percentage difference. We're interested in, what's the actual weight loss difference. Okay, so absolute, leave it as absolute difference. And then it gives you 2 options to input. You can input the raw data, like in number 2 and in number 4. Or you can input summary data. So watch what happens when I click summary data. It drops down a couple of entry boxes, and then I can fill in my stats for the problem, right? Remember, for group A, well, both groups had the same sample size, right? 100 and 100. And this is where I want you to consider that they're going to subtract group B minus group A. Okay, so I'm going to put 9.3, which is for the low-fat diet, and then 7.4 is my group A for the other diet. And so then just fill in the data correspondingly, right? So for group A, the mean was 7.4. What was the standard deviation for group A? Double check. 4.037. And then for group B, the standard deviation was 4.733. And the confidence level for number 1 was 95%. So I'm going to leave that as the same, right? Okay. So I have everything filled out. And then we're going to click calculate. All right. And so it gives us the following. The 95% confidence interval has a lower bound of 0.6807 and 0.31193, which is close to what we got. Let me go ahead and zoom out. We got 0.673 and 3.127. Not that far off, right? Pretty close. All right. So feel free to use this calculator for this assignment specifically, and then if you have any questions still with that, feel free to message me. I know some of you have been emailing me or through Remind. Whatever works best, whatever's been helpful, let's keep using that. What else? I think that's all that I wanted to mention for this problem. Let's go ahead and go to the next problem. All right, so this next problem is working with two proportions. This is going to be number 3 on the assignment. Number 3 on the assignment. And let's go ahead and read it, right? Let's check it out. It says, in the late 70s, there were intensive anti-smoking campaigns, sponsored by both federal and private agencies. Suppose that the American Cancer Society randomly sampled 1,500 adults in 1979 and then sampled 2,000 adults in 1981 to determine whether there was evidence that the percentage of smokers had decreased. Okay, and so on your handout you have the table there, and it has the data for the 2 years. It has the sample size and the number of people who smoked. Okay, and it says for 3A, give a 90% confidence interval for the difference between the proportion of smokers in 1979 and the proportion of smokers in 1981. Okay, and so we're going to use PANIC, the acronym again. And so the first letter of PANIC is for parameter. And so I have 2 parameters that I'm interested in. I'm interested in the proportion of people who smoked in 1979. And my second parameter is the proportion of people who smoked in 1981. And what are we trying to determine, right? We're trying to determine whether there was a difference in the proportion of smokers. Was there evidence to show that the percentage of smokers decreased in the span of these 2 years, right? All right, so step A is still the same as for means. The first step where we ask ourselves, were the samples collected randomly? And yeah, it's stated in the problem, it's given in the problem that they collected these 2 groups of adults randomly. The next thing is, we're going to say it's safe to infer that they're safe to assume that both populations are at least 20,000 people. Right? Where did they get 20,000 from? Well, this is the 10 times n problem. Where did they get 20,000 from? Well, they chose the n value of 2,000. What's 10 times 2,000? 20,000, right? So between the 2 samples that they took a sample of 1,500 and a sample of 2,000. Which one's bigger? 2,000, right? So we ask ourselves, what's 10 times 2,000? That's 20,000. All right. Now, the next step that I want to go into is step 3 of the assumptions. There's going to be a change here for proportions, okay? And what I want you to think about and remember is what type of calculation did we do for proportions when we did one sample proportions? Okay. And so step number 3, we're going to check to see a couple calculations now. Remember, for one sample we would do this pair of calculations, but since we have 2 samples, we have 4 calculations to do. Okay, so we're going to do with the group, we're going to work with the group from 1979 and say there was 1,500 people in 1979 times P1. And the first question when I present this is always, where did you get 0.384, right? For the P1, and actually these are actually P hats. So let me write it on here. I don't know why they didn't come out. But P1 hat comes from dividing 576 by 1,500 adults sampled, which gives you about 0.384. Okay, and P2 hat comes from dividing, and this is the data from the table, 652 divided by 2,000, which would give you 0.326. Okay, and we want to check within these 4 calculations, we want to check, is each calculation greater than or equal to 10? Notice all these check marks that we put, right? So yeah, it ends up that all these values that we calculate are going to be greater than 10. So that gives me the conclusion that both sample sizes are large enough for a what type of distribution? For a normal distribution. Okay. And then the naming of the interval. For this case, right, how many proportions are we working with? I count 1, 2. So we're going to call this a 2 proportion Z interval. Z interval. All right. Now the next thing I want to talk about, one of the last things I want to talk about is the calculation part. What's going to change? Okay. So let's go to the next slide. All right. So since we're dealing with 2 proportions, right? If I write out the formula that we would use for one proportion, if I write it out twice, I have the following 2 formulas, right? So we're looking for the difference of the proportions. Because remember, we want to show evidence that there was a decrease in the number of smokers from 1979 to 1981. So we're going to subtract the 2 proportions, and then we're going to do plus or minus z, the z value, times, and then I put a little animation here, question mark, because remember, we're multiplying the standard deviation. This is supposed to be the standard deviation or error of 2 samples. So I'm going to remind you guys, remember, when we're looking for the standard deviation of 2 samples and they're adding, remember, it's equal to the square root of the first one squared plus or minus the square root, plus or minus the second one squared, everything square rooted. Okay, so why do I mention this, right? Because that's what we're going to look for. We're going to look for the standard deviation of two quantities. So I kind of broke it down over here. And so this is the standard deviation for P1. This is the standard deviation for P2. But we're going to square them, add them, and then square root them. But notice what happens when I square both of these quantities. The square root cancels out, right? And I'm left with these two fractions. Then I'm going to square root this value, leaving me with this result here. So my final formula for step I is going to be the following. And we want to remember that, I just want to remind you guys, P hat 1 came from dividing, let me make sure I get my numbers right, 576 by 1500, which is 0.384. And P2 hat came from dividing 652 divided by 2000, which is 0.326. Okay, and if I plug them in, also notice the difference in the sample size. Remember, for 1979, we sampled 1,500 adults. For 1981, we sampled 2,000 adults. And so you get the following value. And let's look at the conclusion. We are 90% confident that the true difference in proportions is between 3% and 8% higher for those who smoked in 1979 than those in 1981. And again, why do we say higher? It was higher for those who smoked in 1979, which in this case was 0.384. That was our P1. Than those who smoked in 1981. So the way that we work the conclusion depends on how we're subtracting. How you choose your values, right? Some students might choose, 1979 is P2 and 1981 is P1. It's up to you which one you want to choose, but depending on how you choose them will determine how your statement looks. Okay, and so let's see. Let me go back to that website that I showed you guys, and let's see how it would work, how it would look for two proportions. So I'm going to click here for two groups between two proportions and the absolute difference. So I'm going to keep all these bubbles the same, and then let's fill in the rest. Okay, so I'm going to do group A. Since this calculator does B minus A, I'm going to do 2000 first. Sorry, we got a 0. 2000 and then 1500 second. Okay. Input as, let me see, how do I want to input it? Let me put as number of events. Okay, so in 1981, how many smoked? 652. In 1979, how many smoked? 576, right? And let me make sure I get the percentage correct. It's a 90% confidence. Okay, so, all right, so let's try it out and see. And so let's compare. Pretty close. I think it is pretty close. Okay, so this was my 90% confidence interval. And this was my, compared to my answer down here from my calculations. It's pretty close, right? Yeah, it is. And one last thing that I want to show. Let me just erase this marker. But one last thing I want to show is on this website. Let's say I would have put the values differently, okay? So let's say I switch these up. I put 1500 first and 2000 second. And so that changes this to 576. This one changes to 652. 52. All right, so all I'm doing is changing the order of the values the way I put them, right? So let me click calculate and watch what happens. Oh, let me erase this too. All right, so watch what happens. 90%. Huh. $1,500, 576. Oh, my bad. I put 200. Again, I forgot a zero. Sorry about that. Okay, let's try one more time. Calculate. Okay, how does that compare to the answers? How does that compare to these answers that I got over here? Well, for one, they're in a different order, right? And they're negative. Why are they negative? Why are they negative, right? Well, think about it. If I subtract differently, I get a negative number, right? If I would have subtracted this purple value minus the green one, it gives me a negative value. So this is what I mean that to me right now it doesn't matter how you input it, as long as you see that there's some sort of difference. You're still going to come up with the same conclusion, but just keep in mind, right? When we're subtracting, are we getting a positive number between these two or a negative number? Since we got a positive number, I'm going to put my answers as positive answers. Okay. If I get a negative answer in the subtraction, I'm going to put a negative value in my lower and my upper bound. Okay. So I hope this is helpful, and I hope that the website that I'm going to share with you is also helpful. And again, I'll hold another session if we need to through Zoom this time, and then I can answer any questions you guys may have. But thank you for joining me today. Have a great day and stay safe.